Hi, I'm Ken Black. Welcome to Business Statistics for Contemporary Decision Making. Today we're going to discuss how to solve for probabilities using the Central Limit Theorem as it applies to means. The Central Limit Theorem tells us that the distribution of means is approximately normal under certain conditions. And from that we're able to develop this formula to analyze data about sample means. Let's examine a problem to see how it works. A U.S. study of consumer spending reveals that, on average, women spend $558 a year on consumer electronics. That is, the mean amount of spending annually is $558. Suppose that we know that the population standard deviation is also $150. If we went out and randomly sampled 36 women, what is the probability, given this information, that the sample average would be more than $600? That is, what is the probability that the mean for the 36 women is greater than $600, given that the population mean or average is $558? First, let's sketch it out by drawing a normal curve and see what we're looking at here in terms of the probability. Sample means that we know from the Central Limit Theorem are normally distributed, approximately. The mean of the means is mu. In this case would be $558. But the standard deviation of means equals the population standard deviation over the square root of n, which is 150 over the square root of 36. Resulting in a standard deviation of sample means of 25. Our task today is to determine what is the probability that we would get a mean greater than $600 given this scenario. So we're going to shade in the tail because that's the part of the distribution that we're going to solve for. And in the tail lies the probability of our answer. Entering the data into our z formula, we can solve for the z for this particular problem. Our sample mean that we're going to compute on is 600. Population mean is 558. Population standard deviation is 150, and n is the square root of 36. As a result of computing out this z-score, we get a z-value of 1.68. Now we take this z-value of 1.68 and we go to our standard normal z-table and we look it up to see what is the probability of that. When you look up a z of 1.68, you get a value of 4535. We'll put this out here, z equal 1.68. Now the 4535 in our standard normal table is this piece right in here. We're trying to solve for the probability that you have more than 600, so we want to solve for the tail of this. We know from our study of the normal curve that the normal curve is symmetrical and that each half of the normal curve has 0.5000 area in it. So we can come over here and we can subtract our 4535 from 0.5 and we get 0.0465, which is our answer, and is the probability that the sample mean is greater than 600. And the 0.0465, the 0.0465 that we just solved for, is this tail, or this end of the distribution. So we can conclude, if it's true, and given that the average woman spends $558 in the United States annually on consumer electronics with a standard deviation of $150, that only 0.0465 or 4.65% of the time would we get a sample of 36 women who average more than $600 spending annually on consumer electronics. On that same consumer electronics study, we want to look at another problem. We still have a mean of $558 annual spending with a standard deviation of $150. And we're going to go out and we're going to sample randomly 36 women. Now we have a different question. We want to know what is the probability that the sample average of these 36 women would be between $520 and $580. So let's write that up here. What's the probability that a mean would be between $520 and $580? In order to better visualize or understand our problem, let's draw a normal curve and sketch in the areas that we're solving for. So we have a normal curve of sample means. The mean of the sample means, which is the population mean, is $558. The standard deviation of sample means is $25, which we solved for before by taking the population standard deviation and dividing by the square root of n. Now we're trying to solve for the area of the curve, or the probability that a sample mean would be between $520 and $580. Now the $520 falls well below the mean, and the $580 falls above the mean, but not in the same distance as the $520. And so what we want to do is solve for the area between these two means. And as you see in a minute, or as you may know from before, I'm going to hatch them different ways because we're going to put these together to solve for this area. Because of the way our normal curve table is set up, we're going to have to solve this as two different problems. We're going to solve for the area between the mean of 520 and the population mean of 558, and between the second mean of 580 and the population mean of 558. So we're going to have to work out two different z-values. We can pick out either one, work either one at a time. We're going to do the 520 first, minus the 558, which is the population mean, over the population standard deviation over the square root of n, which is 36. And as a result of this, we obtain a z of minus 1.52. Now let's calculate the other z-value. We'll call it z number 2, using the mean of 580. So we have 580 minus 558, standard deviation of the population over the square root of n. As a result of this, we get a positive z-value, 0.88. Now what we want to do is look up each z-value in the normal curve table. And as a result, we'll find that the associated probability value with this is 0.4357. And the probability associated with 0.88 is 0.3106. Now, because these two areas are contiguous, lie together, and because we want those, we don't want the area outside those, we're going to be able to add these up. And when we do that, we get our final answer for this, 0.7463. So the probability of obtaining a sample mean between 520 and 580, given a population mean of 558, is 0.7463. In other words, given the information of this problem, the population mean and the standard deviation of the population, we realize that 74.63% of the sample means will lie between 520 and $580.